implies gradient of f dot b is greater than or equal to 0 for any admissible direction. It's one of the case. If it's 0, it implies it's greater than or equal to 0. Okay? So if we want to find a point, it's equivalent of a solve for x in A plus A transpose x plus, we don't have B transpose here, plus B is 0. Okay.
I have a question. So we're looking at the first order necessary condition.
Yes.
Correct? Okay, so I have written down if x star is a local minimizer, then like that inequality holds. But just because the gradient is 0 doesn't necessarily mean it's a local minimizer.
That's right. So this is the whole point of this problem is if x star is a local minimizer, this condition must hold.
Yeah.
Okay?
Yeah.
But in turn, if this condition holds, it doesn't mean x is a local minimizer.
So it doesn't satisfy.
Second order
It-
necessary.
But it doesn't satisfy the first one because it's not a local minimizer, which is like the hypothesis of like our theorem. I guess I'm thinking of it in like a math context where like you have like if then. So like if something satisfies the theorem, then it has to hold for like the if part and the then part instead of just holding for the second part.
Yeah, but we can have something hold for the second part. The first part is not satisfied.
Okay, so then it doesn't satisfy the theorem.
We want to verify.
You were basically asking us to verify that the backwards direction isn't true.
Yes.
Is that what I'm understanding?
Yes.
Okay, great.
Yes. So we're verifying. So the first order necessary condition says if x star is a local minimizer, then this must be true. So in this problem, we verify this is not correct. Okay. So we solve for x, and we can actually solve this system. So for both 4 and 5, we can solve for x is a 2x2 system, okay, linear algebra. And then we find a point, and we evaluate the Hessian at the point. We evaluate Hessian. And the Hessian is a matrix, so we evaluate Hessian. So we'll find the Hessian, and keep this in mind. So a Hessian, a matrix, symmetric, greater than 0 means, okay, all of its eigenvalue. So all eigenvalue of Q is greater than 0. And this is for any D is not 0, D transpose QD is greater than 0. So these three conditions are equivalent. I mean, given. So given Q symmetric. So I would say, I would add, so Q. So given Q is a symmetric matrix. Symmetric matrix, so all these three conditions are equivalent. So then the rest is we verify, okay, so we evaluate Hessian and we find, oh, its eigenvalue. And we find one of it is less than 0, then okay. So the second order necessary condition isn't true. And I mean, a necessary condition means it's like necessary for something to be true. So if this is not true, which means the point we just find in star is not a local minimizer. Okay? So this is like the point in the homework, you know, we would like to address.
Why does it matter that the eigenvalue is less than 0?
Question?
Oh, wait, is this a second order sufficient condition? Okay.
No, we just, so,
The second order necessary condition.
yeah, so if it doesn't satisfy the second order necessary condition, that is Hessian is greater than or equal to 0. So, for example, so this statement can be equivalent formulated as if Q is not positive definite, its equivalents say that sum of its eigenvalues is less than 0. Okay, so last one is, so for example, for this one is for any direction that this is 0, then this is, so if it's not positive definite, then there exists a direction that this is 0 or less than or equal to 0. Okay? And this direction can be chosen as, sorry, there exists a D that is not a 0 vector. Okay? So there exists a D that is not 0 vector such that D transpose QD is less than or equal to 0. And this D can be just chosen as the eigenvector of a negative eigenvalue. Okay. So once we have verified our matrix is not greater than or equal to 0, this means that the second order necessary condition doesn't hold. Okay, I would say it doesn't hold. And then it tells us, okay, the point we just found is not a local minimum. So this is like the workflow. So now it's back to the gradient descent method. So today we're ready to analyze its convergence. So we are ready to analyze its so we want to analyze the convergence of gradient descent algorithm for this function, that is 1/2 x transpose qx plus, I forgot, did I use subtract over? So this is our f of x. We don't have to add a constant term, because if we add a constant term, it actually doesn't affect where this local minimum is achieved. It only affects our local minimum value. It's like shift our, it's like vertically move our, quadratic function up and down. It only affects, the minimum value. But where it is achieved, it doesn't matter. So we're interested in this, and we apply the gradient descent algorithm is for k that is 0, 1, and until what we call converging, non-converging. So until converging, okay. So this is our gradient descent algorithm is we move our point toward the direction of negative gradient for step size alpha k. Okay. And we call x0 is our initial guess. So this is like a given. So it's a given point. All right. So I'm not sure if you guys have heard a paper. So 3 years ago, actually 4 years ago, okay, I forgot to numbering the panels. So let's start here. Okay, so this is our first panel, the new material instead of the homework. So when you get an interview, you may be asked about this question. Have you ever heard of something called a lottery ticket hypothesis? You know. So actually, this is our lottery ticket, you know, in large scale, non-convex optimization. So if we have chosen a good initial guess, then our chance of hitting a good local minimizer like increases, perhaps, you know, like 10 million fold. So 10 million is an underestimate. Okay, so, but, you know, but the point is initial guess is important. But, so we'll show that in our case, okay, initial guess for this function, initial guess doesn't matter. Okay, so what's matter is this step size. So convergence. So what we want to show is the limit of this is 0. And so the norm, so a norm of x is defined as x transpose x, or we can use other notation like x dot with x, or x parentheses x comma x. So all of these are notations for inner product. Okay. So this is sum of xi square I from 1 to n. Okay. So this is our definition of convergence. And now we will introduce an important tool improving convergence, or in showing an algorithm is heuristic converging. So we have a tool called error equation. Okay, that is we compare. So it gives us a tool. So what is the error equation? So let's first heuristically learn what error equation gives us. Error equation is we try to compare the distance, that is, the next iterate, subtract our local minimizer, okay, with our current iterate with the local minimizer. So this is the error equation. Why want to do this? Because we hope this is smaller than this, right? I mean, both of them are non-negative. So we want this to be closer to 0 than this guy. So this is our next iterate, right? We want our optimization algorithm reaches this point. So this is our goal. And we want our next iterate is closer to our local minimizer than our previous iterate. Okay. So next is the existence of a minimizer. Okay. Because we want to compare this, we have to know our local minimizer exists. So that's why this problem is so nice. That is also why linear regression is so nice if we remove duplicated data points. And for example, if we take a linear model, our instructor will tell us, okay, So let's do a PCA first. Let's remove highly correlated features, and then we remove duplicate data points. Why? This is the case because we want this problem to be nice. So the existence of a local minimizer is guaranteed, okay, for this problem. X star. What is X star? X star is Q inverse times B, okay? And last time we said, okay, so compute Q inverse for a Q that is huge is not realistic, you know. So we want to apply the gradient descent algorithm. Now, let's look at so why this is the case? Because gradient of f, okay, gradient of f, we use a formula we learned. In the beginning of the class, we'll get gradient of f is this, okay? And the Hessian of f is q. Q is positive, okay? So q in this case is SPD, symmetric positive definite. So if q is positive, it just means our critical point is local minimizer. So we set this to be 0. This implies X star is Q inverse B. Okay. And its Hessian is positive, so it's a local minimizer. Now we consider the area equation. Okay. So how do we compute the area equation? Is we subtract our local minimizer on both sides of the gradient descent algorithm. So, I mean, this is a very natural thing to do. Okay. Right. So far, we've changed nothing. We just subtract X star from that equation, from this equation. Right? Now we're going to use a very nice trick. That is, we insert the gradient back to the formula. We know that the gradient at the local minimizer is 0, so we artificially add this gradient back. Okay. Now we use our formula, that is gradient of f of this is qx minus b. All right. So it becomes what? It becomes so at this point the gradient is q times xk minus b, and this is qx star minus b. And b will get cancelled. So once b gets cancelled, we can pull out this q, because it's q multiplied with xk, kth iterate, and x star. So we pull out this alpha k. So alpha k is our step size at the k step, and this is q, and this is x k iterate subtract x star. Now if we look at this, okay, we have xk iterate subtract x star from both terms. So we can pull out again. That is, we rewrite the first term as identity matrix times this. So this is identity matrix. So we can pull out this again. So this becomes identity matrix subtract alpha k, our step size at the kth iteration, times xk subtract x star. And this is xk plus 1 subtract x star. So this is our error equation. I mean, it's not, so it's kind of intuitive, okay? And now what we do is, now we can take the norm. Because we want to compare the norm, right? So they're distant. So the new iterate and the previous iterate, if it keeps shrinking, if it keeps shrinking, then we're in the good shape. Okay. All right. And we want to add a square to it. So now here comes linear algebra, that is.
Excuse me. How did you add that artificial, gradient f to the equation without adding to the other side of the equation?
Because at this point.
Because it's local minimizer. Oh, because it's.
So this is a trick we use. That is, at the local minimizer, at x star, gradient of f is 0. Okay, so now we gotta use something from linear algebra. Okay, so this is like the definition of matrix norm. Okay. So this is like a matrix. So this is a matrix, right? So this is a matrix. And this is a vector. We want to split these two, okay? We want to split because we want to compare the norm of x k plus 1 subtract x star, but we have a matrix here. So we have a definition, okay? So a definition is matrix norm. matrix norm. Okay. So for a matrix that is n by n, so the norm of a matrix, so normally this is, we mean, when we write down this norm, we mean the 2 norm, but so we'll almost all study the 2 norm in this part of the class, so we don't have to add a subscript, but this is defined as, okay, the maximum, let's use maximum because I don't want to introduce supremum, so the maximum of D in Rn, and D is not 0 vector, B transpose AD divided by B transpose D. And this can be also written as max D in Rn. Okay. So we can write this in the inner product form. So that is A times D, comma D, and the bottom is like D norm squared. Okay. Now we'll see why we want to have a square here. Because if we have a square here, it is this matrix square xk. So this is like we have a matrix. So let me derive this real quick. Because it's a symmetric matrix, okay? So for a symmetric matrix times vector square, this is, or, so this is x transpose times x. So this is x transpose s transpose x. So S is a symmetric matrix, so this is x transpose S square x, which equals S square x inner product with x. Okay. So this is a symmetric matrix. Q is symmetric, so this is symmetric as well. Now we just use the definition of matrix norm. I mean, it's literally this AD, right? AD inner product with D equals this. So I mean, we don't have to change anything. Okay. So we should I use this? Okay, so let me use maths. So now let's explain this inequality. Okay. This is taking the maximum over all possible d. That's not zero. Okay. Without loss of generality, we just assume this is not zero. Otherwise we hit the local minimizer. Okay. So this is just one direction. It must be less than or equal to all possible directions. So this is also a very straightforward inequality. We call this. This is called actually Cauchy-Schwarz inequality. So we can use it without proving this again. Okay. Let me write it here. So this is also will be in the formula sheet of our exams. Okay. So that is a matrix times a vector. We take norm is less than or equal to the norm of a matrix times the norm of this vector. So this is called Cauchy-Schwarz inequality, and we don't have to prove it again. And this is actually the case. This is the norm of this guy. Okay. So by definition, this is actually what? This is actually the lambda maximum of this matrix. So the maximum eigenvalue, this is a maximum eigenvalue. Of this symmetric matrix times so the maximum and minimum eigenvalues also can so again we have a lemma. So I think we showed it like in one of our previous class by diagonalization. So if S is a symmetric matrix, okay. So I mean S being symmetric is important because all of its eigenvalues are real now. We can talk about maximum, minimum. Otherwise, we will get a complex number. We cannot talk about that. So if S is symmetric, okay, so lambda minimum of S is the minimum of D in N. D is not zero. D transpose SD divided by D transpose D. And lambda maximum of S is maximum of D in N. D is not zero vector. D transpose SD, D transpose D. So to show how to choose the step size of our gradient descent algorithm, we need one more lemma, that is, okay, that is the eigenvalue of a polynomial of a matrix is the same as the polynomial of the eigenvalue of the matrix. Okay. I mean, so I will show this, but let's just give as an example. So for example, okay, so lambda is an eigenvalue of A, then lambda to the kth power is an eigenvalue of A to the kth power. So this may be talking advanced linear algebra, but I'm not sure if like undergrad level linear algebra has taught this. But then some more advanced is, for example, then 1 minus lambda is an eigenvalue of identity minus A. Okay. So 1 minus lambda square is an eigenvalue of identity minus A squared. And 1 minus lambda, we take the parentheses square, is an eigenvalue of, yeah, maybe I shouldn't use this space anymore. So, but my point is the eigenvalues of identity minus alpha k q square is 1 minus alpha k lambda square, where lambda is an eigenvalue of q. So this is a polynomial of q. This is a matrix. So this is a polynomial of q. So it's a polynomial of matrix, and itself is a matrix, but then its eigenvalue is a polynomial of the eigenvalue of q. And by the way, that result, that lemma, is not restricted to symmetric matrix or anything. It even applies to complex eigenvalues. And so, all right. So now let's look at this. All right. So now this becomes so this less than or equal to maximum of lambda is an eigenvalue of q. Okay. That is 1 minus alpha k lambda so lambda is an eigenvalue of q. Okay. So this is continuum. I mean, that inequality is continued from here. Okay. So it's continuing here. And if we write down the left side, of this inequality, it is the next iterate. The next iterative square is less than, by the way, this is a number now, okay? Look at this. Lambda eigenvalue is a number, okay? 1 minus alpha k lambda, it's a number. This is actually a function in lambda. Okay? We can think this is a function in step size as well once we know, like lambda. So, but we will use some trick to analyze this. So what we hope is this error is, so this is error, which is how close to our local minimizer at the next iteration. This is how close at the current iteration. What we hope is this guy is strictly less than this guy. So we hope this is, okay, strictly less than 1. So what we want to do is we choose alpha k so that this is strictly less than 1. How do we do that? First, we have to analyze this function. Okay. So we hope this is 1 means, okay, we choose alpha k such that this is less than 1. So we have to choose our step size so that this is convergent. So it explains why not all step size will make gradient descent convergent. We have to choose a small step size. So for example, if your academic advisor asks you why your atom doesn't converge, slow down the learning rate. So this is one of the reasons. Okay. I forgot the numbering of the panel, so let's name this panel 7. But, okay. So let's analyze this function. For fixed alpha k. Because we have a maximum of lambda, right? We take maximum of lambda. So we first fix alpha k. So lambda is like so this is like lambda min is equal to lambda 1, okay? This is lambda 2, and blah, blah, blah. Lambda max, okay, equals lambda n. This is a linear function, I mean, almost linear. It has an absolute value, okay? So, what happens is, think about this function for fixed alpha k, okay? When this is 0, it's lambda equals 1 over alpha k, okay? So alpha k is like positive, so it's somewhere here. It's an absolute value, okay? Yeah, I should draw maybe here. Okay, so when lambda equals alpha k, this function is 0, right? 1 over alpha k, but then it's absolute value function, so this is its graph. Okay. And once we fix alpha k, so I'll stop in a minute. Okay. So once we have fixed alpha k, this function's maximum will be achieved at the boundary of lambda. So it's either going to be achieved at lambda minimum or it's going to be achieved at lambda maximum. So it cannot be in between because this function is an absolute function. Linear function achieves its maximum and minimum extreme values on the boundary of an interval. Think about this. So, I mean, this is almost like linear. It's just absolute value. So if we have an interval, we have a linear function, then our minimum is sure on one end, maximum is on the other end. You know, we have no choice. It's a linear function. So even if it's flat, it's still true. Okay. So now this guy equals the maximum of 2 values. That is okay. So next class, we will, based on this inequality, we'll formulate our convergence theorem. That is, we'll just choose these two to be less than 1. Yeah, we'll choose alpha k so that, you know, regardless of where we start, this thing will be less than 1. Then we'll write down the theorem next class. You know, so that's it for today.
If I converted it into this, and just solved it otherwise, is that okay?
Yeah.
Because I could go back and redo it.
Yeah,
what you
yeah,
suggested, but
Yeah, you can do it. Yeah, you can do this. Yes.
Wait, so did you ask if we like put it
the
in
way,
the
yeah,
linear?
Yeah.
writing it as
Okay, yeah.
the
Okay,
equation.
I was gonna
That
ask him.
works
I was
fine.
Yeah,
too,
it's the
cause
same.
Yeah, it ends up being the same thing as just